So moving forward, I request Dr. Shruti ma'am to take things forward and introduce our speakers.
Yeah. Thank you, ma'am. Thanks a lot. Thanks, Prerna, ma'am, for joining in. As this is Golden Jubilee for India Council and a Silver Jubilee for Prerna, ma'am, because it's 25 years of membership she has. So we are celebrating Golden Jubilee of India Council and Silver Jubilee of Prerna, ma'am. Today's speakers, one is Dr. Raghu Selvaraj, who is Senior Member of IEEE. I suppose the voice is being.
Dr. Ashwini, your mic is open. Now, please continue.
Okay. Okay. Thank you. So we have Dr. Raghu Selvaraj, who is senior member of IEEE. He has done his PhD from PhD in power electronics and hydroelectric machine. He has research experience as an academician also. August 2021, he transitioned to the industry and joined PM as power electronics design engineer. He is working as a scientist with electric mobility and tribology research group CSIR, Central Mechanical Energy Engineering Research Institute, CMEI, Durgapur, West Bengal. His research interests are hydroelectric systems, medium voltage industry drives, GAN devices, and he also bagged so many prizes. So we welcome Raghu sir. Next is we have Sharan also, because in during the session only, when Sharan is come up with the case studies, then Raghu sir will intervene. And Sharan is an electronics and communication engineer from IIIT Shri City, where he specialized in embedded system, IoT, digital twin technology. He had the opportunity to gain the practical experience in the area as a digital twin research intern with Middlesex University, UK, where his work involved developing a real-time digital twin for intelligent vehicles. As a part of his honors program, his current research is focused on developing a high-fidelity digital twin for wireless communication links in transportation to analyze and predict their real performance. He is also passionate contributor to the academic community. So I have learned something about from him digital twin. Then we decided, why don't we go with this technology in an open forum with Area Council and with the permission of Prerna ma'am and Ashwini ma'am and team. Like the topic is, as we know, it's a very vast, and he's also a good hands-on. Due to less time, we'll not waste time. He'll just gives the glimpse, and later we'll try to have a workshop with all the hands-on digital twin. So today he'll touch the things of digital twin in 15 minutes. So just share your
Yes,
slides.
ma'am. Yeah. Okay, so is it visible? Am I audible? Is my video clear? Audio clear?
Yeah, you are visible.
Yeah.
Your slides are. You are also visible. You are audible. Slides are also
Thank you,
visible.
ma'am.
So
Okay.
now stage is yours. Audience is yours.
Okay.
So all the best.
Yes, ma'am. Thank you.
Thank you.
Okay, so good evening, everyone. So, yes, I'm Sharan Karthik, and yes, so we'll be diving deep into the along with Dr. Raghu Selvaraj. So, yes, so we digital twins. Like, it's a technology that is fundamentally reshaping how industries innovate, operate, and maintain complex systems. So, yeah. So, before we begin, to truly understand the significance of digital twins, it is helpful to first look at the industrial context they emerge from. As you can see among the timeline that we have just progressed from the mechanization in Industry 1.0 like to the age of mass production and automation. So today we are deep into Industry 4.0. an era defined by connectivity, data, and intelligent automation. So, this is a fertile ground where digital twins have grown. And as we look ahead for Industry 5.0, which focuses on collaboration between humans and machines, the role of sophisticated data-driven tools like digital twins have become even more critical. So yeah. So first, what is a digital twin? So exactly what is a digital twin? The term is used widely. So let's establish a clear definition. Yeah. So a digital twin is just more than a 3D model. So it's a self-adapting, self-regulating, and self-monitoring system. So the key properties to focus here are: first, the symbiotic relationship between a physical asset and its virtual representation. And second, its fidelity and synchronization rate, which are tailored to specific use cases. And third, the most important of all, it supports services that may deliver tangible operational and business value, like back to the physical entity. So it's like a so next, why why DT? So why do we need digital twins? So like the value proposition is compelling. So like DT allows for continuous performance optimization in a like it is very risk free for a human. So a virtual environment, it's very risk free, and they enable true predictive maintenance. It's like moving beyond scheduled checkups to fix issues before they even occur. So what your predictive maintenance does is that like it'll uh, it'll give an exact timeline where an issue might occur, and we may take action accordingly. So yes, in R&D, they may drastically cut down the cost for the need of physical prototypes. For example, I'm in a car crash test. So where we have to make at least 4 cars, and it really depends on the company. So like at least 4 cars needs to be manufactured for them to test its safety. So here the cost is drastically cut down, and also to provide a real-time remote window into physical operations. So, for example, if any environment is very inaccessible, or if it's hazardous.
Wait a minute, Sharon. Sharon, just wait a minute. All the all the please mute yourself. All the participants, please mute yourself. Okay, Sharon. Sorry.
Yeah, it's fine, ma'am. So yes, this optimization leads to increased sustainability, and it also reduces the waste and also energy consumption. So yes, finally, as an enabler for Industry 5.0, they support the concept called N equal to 1 manufacturing, which is like highly customized to every customer. So, like for example, let's take a Rolls Royce. So, what they do right now is, depending on the customer's needs, they may customize each and every one of their cars. And so, similarly, we can achieve such a customization in a mass production kind of setting. The factory knows which customers need which kind of features in that product, and then manufacture accordingly. So is so that like every single unit is produced efficiently. So like each building, as you can see, it'll like it contains separate models for each buildings and each areas. So is here you can see a slight a small video where you can see it in action. Yeah. So if you were to have a look, we'll share the slides after some time, and like the sources for all the resources and videos is just embedded either inside the image itself or as a separate link. Cool. Next. Yeah, here's an example from MATLAB themselves. So this is an example on oil and gas rig. So in the oil and gas industry, assets like a drilling rig, they are very complex and they operate in extreme conditions. So like for instance, they are installed in very remote places where multiple is environmental catastrophes may occur. And like to predict some of those, we need to know different parameters. So here, this digital twin is built on MATLAB, specifically Simscape. So this model is a system of system. So as you can see here, as the from the genset system and subsystem example, like each block has a sub block which is modeled for a specific use case. So like to simulate different aspects of the system, we'll first segregate it into different small systems and then combine them to into a bigger system, which will give us like a holistic view on each different parameter. So yes. Next, we'll move to the digital twin of digital twin in healthcare. So yes, so we're creating a patient-specific heart models for medical scans. Doctors can doctors can just simulate different surgical procedures, and they also can predict treatment outcomes. So this will help them like accelerate the diagnosis and help stratify the patient risk. And it also represents a monumental shift towards precision cardiology, where treatments are tailored to the individual. So depending on each patient's history and their symptoms, it's like yeah, just a customization in the healthcare industry. Yeah. So next, okay. Now here's an interesting example where yeah, Siemens and Nvidia they collaborated to create industrial metaverse. So like by connecting Siemens accelerator platform with Nvidia's Omniverse platform, they enable the full fidelity digital twins of entire factories. So you can see on the right side it's the physical factory, and on the left side it's the DT of the factory. So like this allows for uh, in-depth immersion and it's real-time collaboration across the entire product lifecycle, right from design to operation. And like the employers can view from cloud what's happening in the industry, and then they can also whatever like changes they make in the virtual environment, it is makes it reflected in the physical environment. And yeah, from here on, Dr. Raghu sir will continue. So over to you, sir.
Thank you, Sharan. I hope my audio is clear.
Yes, sir.
And
Yes, sir.
yeah, thank you. I welcome all. So let's. Sharan has given the some sort of idea about the digital twin. So basically, we will look into a digital twin scope in automotive industry, particularly. So as already we know that one digital twin is a virtual replica of the physical system. So, as an electronics engineer or electrical engineer, we know multiple softwares we will use, like LT-Spice, P-Spice, MATLAB, and everything. So that is a simulation-based software. When you're going to fabricate the hardware, the results will be somewhat little bit different. When I'm talking about electronic circuits with a MOSFET ringing circuit or any oscillatory circuit, the physical circuits will be having some sort of a noises will be there, some sort of oscillations will be there, second order waveforms will be there. But in your simulation part, you don't have that much. It is going to be a pure filtered waveform, you will be getting that part. So when you're going to think in that manner, are going to connect your physical system data with your simulation system. So that is the major part of your digital twin. So particularly when you focus on a automotive industry, it is moving towards the electrical vehicle. Okay, so in the electrical vehicle sector, you can see we are going to have a motor is there, and then inverters will be there, charging converters will be there, like from 400 volt to battery, because from the grid to battery, it is going to be 400 or 800 volt systems will be there. Small electronics converters will be there from DC to AC. Like if you're going to have an audio system, it needs a 12 volt from 400 volt battery. When I'm going to have a inverter to drive the motor for the wheel, so it is going to be have around 400 volt DC to convert into a AC to run the IPS motor or BLDC motor. And even though so many electronic parts are available, it includes passive elements. Like you can think about the inductor will be there, capacitor will be there. So when I'm talking about this inductor, capacitor, and semiconductor devices, it always the reliability first comes into your question, because the reliability is one of the part. Okay, the reliability is the one of the part. We will look into the reliability, the how much the user will be operating. Like some of them will be drive the vehicle smoothly, some of them will be drive the vehicle hardly. So based on their user capability, the entire things will be changed. The degradation of the electrical components will be changed. Someone will be use the rough driving. So that's why we need a digital twin in your automotive industry to get the data from the different kinds of user to make a rugged system. So that's why you can see in the left side there is a physical system. It consists of sensors, intelligent controllers, and everything. We will keep on monitoring using the sensing data. That means we convert the data, digital data, to our virtual simulation space, and using a artificial intelligence or 3D CAD model. Like I will simple example when I'm talking about the heat extraction from the electronics components. You can't really see that one when you're going to have a, physical system. What you want to do, you want to take the data from using a sensors, then it will be infused into your digital simulation space, and you can see how much is the wave, how the heat wave is coming out from the devices or capacitors or inductors, how we can reduce that one, what is the efficient manner to design the ventilation for that one, like forced air cooling or that things. And even though simple example, you can take it as a battery. So battery is having a state of health. If the different user will be having a different state of health will be projected. So automatically what will be happen, if you are going to have a use the vehicle in a rougher manner, it will be draw more current from the battery. So automatically it will be reduce the lifetime of the battery. When you're going to have a smooth user, he will not drive rough. Means he this is going to be have a small amount of current, and the nominal amount of current is he is going to draw when you're going to press the acceleration of the vehicle. So automatically, what will be happen? The state of health will be going to be a higher, and then useful lifetime also of the battery is also going to higher. So each and every time, because when you're going to talk about this one, this is entirely related with your so many applications, like insurance. One insurance company want to know how the battery degradation has been happened. And then when I'm talking about the vehicle manufacturer must be know, because he is claiming my battery pack is having a lifetime of 10 years, but due to some operational issue, it may be coming to 5 years. Again, the company will be comes into a huge losses for that thing. So these parameters only can be applicable to the digital twin only, because when you push the our things to a digital twin, we can get the enough data. That enough data will be used by industry to make a rugged system to climb their data sheets. So that is the one of the basic thing when you're going to talk about the automotive industry. Saran, shall we go to next slide? Yeah, when I'm going to talk about the digital twin architecture for this particular electrical vehicle, so first one is to be you are having a hardware, like it is to be an inverter or a DC to DC converter or any part of an electronic system that needs to be fed with your sensors and actuator to collect a high fidelity operation data. For example, I can get data from the battery temperature, motor current, and then a semiconductor temperature. These things and all I will be get from that one. And then it must be having a communication layer. It must be having a both bidirectional communication layer. Like you need to share the data from your motor or battery to your virtual system by using a bidirectional communication layer. For that one, you can use cloud-based or edge computing or something like that one. Then you are going to use the hardware in loop modeling simulation. Now, recent days we are having a so many companies are coming with the HIL platforms like Typhoon, all the things like DSpace. Everybody is coming with a HIL loop. So we will get the data from that. Uh, I hope my internet is having issue.
No,
So
sir, you are audible, sir.
yeah, okay.
Please
I actually
continue.
got some messages like this thing. Okay,
Someone
then
is
you
asking like your voice is not clear, so that's why I'm replying. Please check your internet.
okay, okay. So then you're going to have a digital layer that converting into that part and data processing, because there are a huge data you will be get it within a minute. You want to filter out the data and then you want to identify which data you required for the analysis, because when you're going to compute the Fourier transformation, you will get so many data. How to limit that data? So that is the important for that data processing layer. Then you are going to create an application layer. It should be visible, like 3D modeling, how the heat waves are flowing through that thing. That things and all you need to go. So when you're going to talk about the digital twin architecture for the electrical vehicles, these are the applicable things. So you need to have a physical layer, communication layer, and digital layer, and data processing layer, and application layer. This covers the entire digital twin mod for your things. Next, Sharon, shall we go for next slide? Okay, so I'm basically from Powertronics. So I would like to give some part of a insight where we are going to have. So first thing is to be a powertrain electrical vehicle, and then next is battery management system. So wherever we are facing the problem, the thing is electronic components reliability. We can't never justify the electronic components, even though you can see in the motor wise electrical motor, everybody will be claim there is a 10 years warranty in your home appliances. Like you can take your AC or washing machine or a fridge. When you're going to have an electronic circuit board, they will give 1 year or 2 year warranty, because it's entirely depend upon your operational environment. So how you are operating, because the same inverter when you're operating in a Rajasthan, it is going to be have a different environmental condition. The same thing you are operating in a Himachal, it is going to be have a different environmental impact. So when you're going to start to design your vehicle, you need to have this electronics part should be evenly take care. And apart from that one, when I'm talking about the capacitor, this is the one thing, because when you look at the like you go to the data sheet of a capacitor or semiconductor devices and inductor, the particular point of the temperature they already mentioned in your semiconductor devices. Like you can take any semiconductor devices from manufacturers like silicon carbide or silicon or gallium nitride or any MOSFETs, BJT, JFET. They will having a certain operating temperature, and then capacitor also, it's having a certain temperature range. Even though you analyze with the capacitor, they will tell for electrolytic capacitor, the maximum aluminum electrolytic capacitor, the maximum is 105 degrees Celsius. But as per the lifetime prediction, if you going to keep on operating with a 70 degrees Celsius, it will be give a 10 years of lifetime as per the data sheet. But if you increase the 10 degrees Celsius, it will become into half of the part. That means it will become into a 5 years. If you keep on increasing your temperature of the capacitor during the operating condition, or it is taking a huge surge current due to the demand of the user, then automatically the reliability of the capacitor will comes into a question. The same parameter for your semiconductor devices, because we as a we go to the any world in the world, everybody will be get aged, their performance will be decreased. The same for your electronic components also. If you're going to have a semiconductor devices, if you're going to have a capacitor, if you're going to have an inductor, the performance degradation will be happen. When the performance degradation will be happen, when we need to change and when we want to replace the component should be identically user need to know, otherwise it will be cost a huge damage for the system. That's why we want to work on the prediction of the electronic components like power electronics one thing, and then battery management system. I already told how the user is charging, whether he is continuously putting for a fast charging of the vehicle, or he is going to go for the normal charging, because nowadays everybody is in the rush movement. We need a fast charging of the vehicle. So we will go and we will tell 2 hours we will fully charge the battery and we will travel towards the some distance. So how that will be impact your system and how it will be impact your reliability, because I can't give assurance my battery will become for 10 years with a solid performance, or my controller part like power electronic circuits like converters, inverters will become for a 5 years or 10 years. They will tell 2 years I will give a minimum warranty. After that one, you need to have a if anything is happen, you want to change by your own yourself. So that is the thing where the digital field comes into your play when you're going for the reliability part. Sharon, shall we go next one? So these are the things we can have a entire overview of Polytronic architecture. So already I have explained that one. So the major thing is that one you want to work it on digital twin is the thermal management of the system, because this thermal will be impact everything of the electronic devices, electronic components. So that is the one thing. Everywhere the thermal will be impact how you are operating that one. Because in our present today, the climate change is huge, because when we see in last 10 years back, the climate is somewhat different. We will get it around 25 or 26. Now it is going 36 due to that entire emission of that one. So this is creating a thermal management system. In future, the temperature keep on increasing. How our electronic system will be having the reliability. So that thing is the major point when you're going to talk about the electronics part. Sir, next we can go. A simple example when you're talking about that one, as I consider as a electronics part. So one is to be a MOSFET. We usually use so many application this MOSFET. Like recently we are using for some sort of a converter circuit also, like audio amplifier also, and so many electronic circuit we will use. What is the major thing in the MOSFET is to be what is the electrical behavior, another one is a thermal behavior. When you're going to turn on the MOSFET, you need a certain condition like there is a we are going to be have a charge the capacitance between the gate to source, so that will be that will be trigger your MOSFET to turn on, and then you want to turn off the MOSFET, you want to discharge that part, and then same time there is a losses associated with the MOSFET. So that is to be a like conduction losses and switching losses. Usually the semiconductor itself is having a some sort of a RDS on. That means static resistance will be available. When it is going to be the on condition, that RDS on will be somewhat into I square will be give the conduction losses. The same the conduction and the switching losses in the sense when it is going to be turned on, there will be a switching losses will be occur. Apart from that, these two things will be transferred into a thermal behavior, like how much time it is conducting. These losses is going to be have a thermal network. So when you're going to take the data sheet, okay, data sheet is tested for some reliable condition, but it is not for your practical application. Your practical, when you're going to put this design your MOSFET and you make a PCB board and start to experiment that one. No, we usually call it as a magic fire. That means every time the first attempt, your MOSFET will be burned out because we didn't consider the thermal aspect of the MOSFET, because we didn't consider the how to cool the MOSFET. What is the range we want to operate? We didn't decide. So these parameters will be keep on burning your circuit. So in view of that one, how we can do in the physical system, because physical system when you're going to add a sensor to your MOSFET, there is a, you can see that one, there is a body is to be a like aluminum shape will be available in the MOSFET. When you really see the MOSFET structure, that you are going to have a thermal paste in between that one, and you are going to mount with your aluminum heatsink. You need to insert your sensors between that aluminum thermal paste and then your heat sink. The sensor, what will we do? That sensor will be not capable to get the entire data. What will be happen? It will be transfer a small amount of data and it will be give a voids to your MOSFET. So due to that one, that whatever the thermal energy generated during the operation of the MOSFET will not entirely transfer to your heat sink. So that will also cause a problem. So how we can do that one? We can using a digital type of a modeling, and virtually we can see how much is the heat dissipation will be happen in the MOSFET during the different operating condition by making a various ambient temperature like your room temperature or environment temperature you are going to create virtually, and you are going to analyze how the temperature of the MOSFET is getting from the, like you can use an ANSYS tool or COMSOL, whatever may be. You want to create your physical model data, like you can get a IDS value, VDS value, and everything from you by putting a current sensor in between the drain to source, all the things, and get the data and simulate in your this electrothermal platform like ANSYS or COMSOL. Then based on that data, you can see the virtually how the heat is generating in the MOSFET, what is the temperature range is available in the MOSFET, then how we can extract. Based on that extraction, again you can made a heat sink. Based on the heat sink also virtually designed, and you can make a like how much pressure and then volume of air you should be pushed for the forced air cooling of the MOSFET to extract the heat from that part. So that is the one of the major focus we in the digital twin we will be getting that things. So next, Saran, can you go next? Yeah. So what will be that? So when you're going to have a this type of, I told you so many things are there, but to do that one, you need a particularly you need a high fidelity system, because when you run the ANSYS, backside it will be run the Newton Raphson method. It will be take 1 hour or 1.5 hour simulation. So this type of system needs a high stringent requirement of high fidelity and then low latency, because it need to be match with your physical system, because physical system in the sense, if I am switching on my MOSFET with a switching frequency of 100 kilohertz or 100 megahertz, the same type of computation can be done on my simulation parameter. Otherwise, what will be happen? It will be run on different sampling time. It will be run on different sampling time. So entirely the data mismatch will be happen. I can't get the real time what is happening in the physical system cannot be observed in my visual system. And then computational efficiency, how fast it is computing the mathematical calculation, because it is a physical equation we are going to give an input to solve the that one in your my simulation. So how fast it is having a computation efficiency to match with my physical system, and then how fast it is computing the algorithm, any algorithm I am putting that part. Okay, next, go for next slide. Here's a simple example when you're going to talk about MOSFET. First, you need to get a data acquisition by getting an IDS value and then VDS value, gate to source voltage, and then case temperature of your MOSFET. That raw data we are going to transfer into your virtual model to align with your physical devices. Like same parameter, like you can go with the LT spice or P spice, you can model that parameter with a huge number of data, and then there is a parameter estimation will be done. So when you're going to operate a 5-year-old MOSFET, how the losses is occurring, according to that one we are going to calculate the what is the change in your on state resistance value, what is the change in your Dunson temperature value through electrothermal model, and we are going to based on that parameter we are going to find out the degradation, like means how much here it will be fully degraded, and we are going to estimate the remaining useful lifetime time, and we will start to have a flag the potential failures. For that one, you need to replace this MOSFETs, or you need to replace the entire circuit, you need to replace the entire capacitor or inductor. That things we need to inform to your user. Then only timely action will be save him a huge financial implication for the changing. Yeah, go for next slide, sir. This is the simple like model, we got it from that one. So particularly when you're going to have a physical system, and then we are going to get a digital by using a different types of sensor. So you can use a thermal sensor, current sensor, and everything. You will acquire the data from that digital data, and you are going to have a virtual system. You transfer that data to your virtual system and store it, and you will analyze that one. There is a again discrepancy will be come into your picture. Then again you are going to get again, this is a continuous feedback loop system. Every time you want to get the data and you want to match with your physical system, that will be give you the prediction. That means you're going to use your own algorithm to identify predictive maintenance, performance optimization, how to use the enhanced reliability. Like we usually in your cars or two wheelers, we know so that one when you operate within the 20 to 30 kilometer per hour of the speed, you will be get eco mode. Then you are going beyond that one, it is going to be at that one. That means when you're going to have an electronic system is getting degraded, it can be suggest you. The thing is that one you operate within a certain part of the speed limit, then your particular electronic system will become for another 2 years or 3 years. So this is the thing is needed for the future to enhance our reliability. That's why, for example, you can see what are the parameters implicate the MOSFET. First one is the capacitor. MOSFET is having a CGS capacitor, CDS means capacitor across the gate to source, capacitors across the drain to this one, capacitor across the gate to drain, and then drain to source. These capacitor keep on degrading when it is going to be have a higher lifetime according to the thermal implication. Then heat extraction from the MOSFET, then RDS on means it is having a huge lifetime, means after 5 years the resistance value of the RDS will be keep on increasing. This parameter we don't get from the anywhere from the data sheet. So for that one, you need to make a physical system and keep on running for a 1 year or 2 year. We want to record the data and we want to analyze that one by using this much amount of current variation. How much is the degradation happening in my capacitance of my MOSFET, and then there is a how much the resistance value has been increased compared to the data sheet value. That can be only give you the remaining useful lifetime of your MOSFET and other electronic components. These are the application oriented for the digital twin in the power electronics. I hope I have given some sort of a case study to where we want to work on that, particularly in that one, because there is a data sheet and then this one is having so many discrepancies will be there when you're going for a physical system. That should be that should be taken care only by digital system. For example, recently I gone through the one of the simple example. GE has made a jet engine with a digital twin with the help of Infosys to predict the lifetime of the jet engine, how many hours it can be operated because on the various conditions. So these are the industries looking for that part of the system to predict the system. I will hand over the session to Sharon to take over that part. Thank you.
Yes, sir. Thank you, sir. Wonderfully put, sir. So, okay, so yeah. So next we move to the tools and resources. So like all these case studies, and also yeah, if you want to build a digital twin for yourself, or as an application in any of your your research or in industry, there are multiple tools and platforms which enable us to do this. So yeah, so let's dive in. First, MATLAB. So it's a versatile tool. It's extensively used for building models that that is used in a digital twin. So with its with its toolboxes for statistical analysis and its predictive maintenance, and also with the power of Simulink, which is used for system simulation. It's really a yeah, it's a cornerstone for many applications in the field of engineering. So yes. Next we come for Unity. So Unity and like a very similar platform like Miss Unity is Miss Unreal, but Unreal is a bit complex to use for the beginners. So yes, I'll just stick with Miss Unity. So like they all fall in the same category. So in platforms or rather Miss game dev engines like Miss Unity, you can create very detailed virtual environments and integrate Miss real-time sensor data, and it's really very customizable using the C# scripts and everything. And you can model different aspects of the real world physics. Uh, yes, for instance, gravity, electromagnetics, and then rigid body dynamics, which include friction and torque, and then fluid dynamics, along with soft body dynamics and of course thermodynamics. So this is like the beginner platform if you want to just create a basic virtual environment. So you can also we can also pair it up with your Blender. So there we can create very detailed models which can be imported into Unity to perform simulations, or if you want to just create like digital shadow, which is nothing but the real time replica of our physical asset. So whatever is happening in the physical asset, it will be reflected in a shadow, digital shadow. So next comes the NVIDIA is investing a lot in these technologies where they enable us to develop algorithms uh, for different types of robots actually, and also with collaboration with Pixar and multiple other leading industries. They've also created Open USD, which is like it's a universal scene descriptor. So where you can create very detailed virtual environments, which is like a mock-up of the real world. Like the physics there is it's just immaculate, and it's much more accurate than a game engine. So inside Omniverse, we can perform multiple different simulations, and also we can also use Isaac Sim as well as Isaac Lab to perform reinforced learning. So it's like the robot learns inside this virtual environment by trying and failing until it gets a reward. And so next, yeah, Siemens. So like Siemens, they are like very interesting. When it comes to digital twins, because they offer one of the most comprehensive DT solutions. So like they focus on covering like entire product life cycle. So like they focus on creating executable digital twins, which are models that don't just represent an asset but can actively simulate your behavior in real time.